Hello, welcome to SELinux Mandatory Access Control Mechanism presentation. Ifan Yodiaka. In this presentation, I will begin by first going through what SELinux is, a look at the architecture, the policy framework, and finally some of the utilities of SELinux. So yeah, we can proceed now. So, so we start by actually asking what is SE Linux? What actually is SE Linux? Security enhanced Linux. Well, it's a security model built into the kernel of the Linux. It represents the implementation of a role-based access control, a dynamic type enforcement developed by the NSA. In SELinux works like a least privilege kind of policy where a process is given the necessary requirement or necessary resources needed to perform the function effectively. And so it doesn't have the power, the root user that have the power to do almost everything on the Linux, but with SELinux, a root user doesn't have such powerful access or powerful control over the OS. And like other OS model that maintains the user's right to take decision whenever a user or a process access an object. But in SELinux, the users cannot override the behavior or the decision of the operating system. And it's important to know that SELinux is not actually built to replace antivirus or to function like an antivirus. That is not a function, neither is it built as a form of a firewall. Yeah, so this is what we call the flags architecture in security enhanced Linux. So it provides two policy independent data types for labeling. So we have the security context and the security identifier. So to make an object understand the security policies that it follows, we need to have a security context. So and security context is a variable length string which can be interpreted by any applications or user with an understanding of the security policy. So as like we have on other security or other operating system, we also have the security identifier, which is defined by flags and is a fixed size value which can be interpreted only by the security server and is mapped by the security server to a particular security context. So using this security identifier, the policy enforcement code can make security decisions concerning any object, just like the architecture showed. So it has three primary components: the security server, the object manager, and the access vector cache. So the primary goal of the architecture is actually to provide flexible support for security policy by ensuring that the subsystems always have a consistent view of policy decision regardless of in whatever way those decisions are made or how they might change over time. So to achieve this goal, the Flags design makes a strong distinction between security policy decision making and enforcement function. So here the object manager, which kind of, as you can see here, houses the policy enforcement and the AVC. So the object manager is actually responsible for enforcing the policy decision. It contains security policy decisions and then applies and how they applies to identify and control access to objects. And what the AVC does, which is the asset vector cache, it's used to store access decision made by the security server for subsequent access check. This helps to improve performance. So when a request is made by a client or an object trying to access a resources, the object manager queries the security server, which houses the security policies, and then make decision based on the context in the security policy pertaining to an object that's trying to access that resources or that process. So by making the decision, whatever decision that is made is catched at the access vector cache. So by that doing, whenever a decision or whenever that particular object is trying to access a resources, just the same resources or process, it will look at the AVC rather than going to the security server to check the policy. So because the AVC have already catch the information or catch the decision making based on that, it just from there it just makes the decision if the object if the object manager will either deny the request or it will accept and grant the request. So that is actually how the SELinux makes decision based on an object requesting access to a process or to a resources. So I'll take a further look on how SELinux actually implements policies. So what SELinux like the SELinux server, the security server is actually responsible for consulting the security policy to guide itself by knowing the rules, whether access should be allowed or not. So the security policy defines types when they are associated with files, and these types are called we call it domains when they are associated with a process. So the SELinux security policy is a system-wide policy, like I mentioned previously, which contains all the rules, e.g., like what domains can actually access what types. So the rules in the policy can be modified according to the specific security needs of an organization or maybe a policy, and the policy can actually be written from the crash, can be created or created by anyone. So by anyone. So due to time, I've already explained the function of the security server and the access vector. So, but I've not actually talked about the SELinux hook. So actually, what is SELinux hook? So what it does here is the hooks are put into the kernel manually, and therefore hooks are actually embedded into the kernel. The hooks are functions that comes into effect when an access attempt is made. So the hooks obstruct the kernel normal flow and goes on to make an extended access control decision or request. Decisions are then made by SELinux security server. So let's take for example, the access control checks that the security server, like whether a process has access to a file, are based on the security context of that file, which are defined in our security policy. Okay, so the security context is a label consisting of an SELinux user, a role type, and optionally, occasionally, there is also a level. Okay, so the security server consults the security context to ensure whether the process trying to access the resources has any access rights or not. The process itself has its own security context. And now, the security server takes this access decision based on two things. First, the process that is accessing the resources usually always has a security context set with it, and the resource being accessed also has a security context set. So the security server consults the SELinux security policy, and then based on the rules imposed, it determines whether the security context of process can access the security context of the resources which is being accessed. So, have it in mind that all of this process is done when the access permission is checked and allowed by the discretionary access control system. Because the SELinux is actually built on the Linux is built on a Linux. So it first checked the discretionary access control if it's permitted or not. So if the process in the DAC is permitted, then this process can be done. But if DAC denies access to a file, the process gets terminated in that point, and the SELinux checked for that process are not done at all. So it must first pass through the DAC before actually even getting to the security enhanced Linux implementation. So SELinux have three policies created, and these policies were actually created based on security needs. So here we have three policies that is in Red Hat Enterprise Linux operating system and the Fedora. So due to time constraint, I'll try to see if I can just give a brief view into the three policies. So we have the SELinux targeted policy, which is default on both Red Hat Enterprise Linux operating system and on Fedora. So we have the minimum policy and we have the multi-level security. The SE Linux targeted policy, which is default on both the RHEL and Fedora. So under this targeted policy, each subject in the system and all objects run in what we call the unconfined T state, except those daemons which are targeted. That is why this policy is named targeted, because it targets only specific daemons. Those objects would be in the unconfined C domain. There will be no restrictions on them, which means they are same as like using the standard Linux security system, which is the discretionary access control. So those system daemons which are targeted by these policies, they are separate domains made for them, and each of them would run in their own domain, which of course is confined in its level of permission it would have, and it would be stated in this targeted policy. The SELinux minimum policy has been built exactly the same as the targeted policy, but the major difference is that the minimum policy installs just as the base policy package. So almost everything on the system will run as either intrigue or unconfined, which means all the domains will run unconfined. Well, this policy is actually best suited for someone who just want to start with SELinux policy system and to get familiar with it. And the last policy is the multi-level security policy, which is also an implementation of mandatory access control system. And so it's supported by the SELinux using SELinux policy, MLS policy in the Red Hat Enterprise Linux operating system and Fedora Linux distribution. It actually uses the Bell LaPadula model, um, which is the standard model of the MLS policy. So here the MLS focuses on confidentiality. The access to resources allowed based on multiple classification of information, and also managing multiple users with varying levels of information clearance, just as we learned with the Bell LaPadula model. Unfortunately, I'm running out of time, so I'll be a little bit fast here. So I'll just look at some of the SELinux utilities. We have the new role. So what this does is it starts a new shell with a new role type or role and the type combination. And we have the chcon. It changes the security context of a file directory or an object. And we have the check policy. This checks the security policy and compiles it into a binary form suitable for loading into the kernel. So we have the load policy. Using this, the compiled policy is loaded into the kernel, into the running kernel. So we have the get enforce, used to get the policy enforcement, which returns either enforcing or permissive mode. It always returns enforcing if the kernel was compiled without SELinux development support. Then we have the set enforce. This sets the kernel to either enforcing mode or permissive mode. And then we have the set files. This sets the mark labels on directories and files as is defined in the system security policy. If the target being supplied is a directory, all the files associated with the directory will be labeled. So thanks for listening and have a nice week.